Okay, just one more video on guessing games with geometric sums. Try to get to the general formula here. Lots of examples now. The original 2, the sum of powers of 2, the sum of doubled powers of 3. Well, kind of like when we went from the 9 plus 9 to the 1 plus 10, let's just figure out if we didn't contrive that first term to be so special, but you kept the r equals 3, for example, what could we conclude on this? Well, here's where we want to leverage what we found here and not try to just do it from scratch and guess from scratch. Guessing is wonderful, but you also want to capitalize on what you already know. And all we've done these are the doubled powers of 3 added up. If I'm going to add up the powers of 3 not doubled, that's just 1/2 of the original thing. So that's just 1/2. We've just divided this side by 2. So this guy is just going to be divided by 2. Interestingly enough, that means that 3 to the n minus 1 has to be an even number, because this is clearly an integer. It's not going to be something over 2. But that's pretty obvious in this case. 3 to the n is going to be an odd number. Subtract 1, you're getting an even number. In other cases, it's not as obvious that you're automatically going to get an integer, but you will. Okay, so there's another example. The sum of the powers of 3 is once again the next power of 3, subtract 1, and then divide by something appropriate. Okay, so now we're starting to see the pattern. This can be written as a 10 minus 1, because the 9 was not random. The 9 had to match with the 10, and it's because it worked because it was 10 minus 1, is the base of our number system, minus 1. Here, this is a 3 minus 1. Okay. And this one, this also is 2 to the n minus 1. That's over a 2 minus 1. That's why this was so special, and we didn't have to do something besides 1 here. 2 minus 1 is just 1. Okay, so we're very, very close to a general formula. Let me just do a couple more where we keep playing with this first number, the A1 number. What if you had 7 plus 21 plus 63 plus, I'm just going to write it as 7 times 27 plus 7 times 81 plus, so this is getting pretty general, pretty random. I did not contrive, for once, I did not contrive the 7, this initial number, to be special with respect to 3. And I also didn't choose it to just be 1. Okay, well, what are we going to get? Same idea. Good time to pause the video if you want to do it yourself. But same idea. All I did was I took this side and I multiplied it by 7. And that really is how to get the general geometric summation. If you know how to do a geometric summation that starts with 1, which I think we're pretty close to writing a general formula down for, then you know how to do it if it starts with an arbitrary number, because that's going to be a common factor in everything. The way geometric sequences work is because everything's based on this by repeated multiplication by 3. I've just multiplied everything here by 7. And so that's just going to be 7 times 3 to the n minus 1 over 3 minus 1. Okay. One more. Let's multiply this guy by 7. 7 plus 70. That's a little easier to do by hand. 7,000 plus 7 with a bunch of zeros after it. 7 times 10 to the n minus 1. In other words, that's just 7, 7, 7, 7, 7, 7, 7. Like this was 1, 1, 1, 1, 1, 1, and this is 9, 9, 9, 9, 9, 9. So what's an interesting fact about 7, 7, 7, 7, 7, a number with a bunch of 7s in it? Interesting fact is you can create it by first doing this cool thing. Take 10 to the n minus 1, which gives you the ones with 9s. Cancel out the 9s by dividing by 9, and then just put the 7s in by hand. Okay, and that's going to give us our final answer. I can erase everything but the last couple. Looks like what we're getting, it's not what you'd call a proof, but it looks like what we're getting is if you start with A1, and then you keep multiplying by r repeatedly, and then go up. We usually call n minus 1 the last power of r. It's looking like you'd have A1, like the 7, times the next power of r, which conveniently is now n, so that's kind of pretty, minus 1, and then over r minus 1. And that indeed is the master formula for the sum of a geometric sequence. And it's not a proof, but it's not hard to go from this, once you've got the formula, to say, oh, how could I prove this? Basically, just multiply this all by r minus 1 and show that you get the top of this guy. And that's in another video anyway.